Okay. All right, everybody, let's get started. So last time we talked about the MAP rule and likelihood ratio test, right? To the maximum a posterior decision rule. So this MAP rule is characterized by a so-called likelihood ratio test. So we call it LR test. The likelihood ratio test is the follows. We look at likelihood ratio, where it's the ratio between the conditional PDF of your observation given your hypothesis. Yeah. So under two different hypotheses, suppose we are doing binary hypothesis testing. Under two different hypotheses, we look at the ratio between the conditional PDF of the observation random variable. Now, if this ratio is, we compare this ratio with the ratio between the prior probability of these two hypotheses. If it's bigger than this threshold, then we decide H1. Okay. Meaning that the numerator is more likely to happen in some sense. Right? If it's smaller than this threshold, then we decide H0. This is the likelihood ratio test. And in some cases, if this threshold equals to 1, if these two prior probability are equivalent, then we call that the maximum likelihood test. So in that case, this threshold is 1. So we just look at the likelihood that achieves the maximum one under that corresponding hypothesis. So it's called maximum likelihood. But in general, we need to compare this likelihood ratio with a threshold determined by the prior probabilities of these two hypotheses. So last time we looked at a bacteria example. So let's look at another example in the communication applications. So we are sending out two signals. Through a communication channel. This channel can be wireless, can be wired. But on the receiver side, we receive a Y, random variable signal Y. And this could be, so suppose the transmitter sends a signal X. All right, the X can take either -1 or 1. So we have two different hypotheses. Now X transmitted through channel and we receive Y. Well, Y is a noisy version of the X. Okay, it's a noisy observation of the original signal. Now we need to decide by observing Y, we need to decide which hypothesis to take. Basically, we need to decode the observation into a corresponding hypothesis so we can decode the message. And here we can use, so let's assume these two symbols are transmitted equally likely. And let's further assume that under the hypothesis H0, which means if we transmit -1, if we transmit this signal, then Y, the observation follows a standard, a normal distribution centered at the message -1 and has a unit variance. Okay, this is a reasonable model, right? The observation is a noisy observation of the original signal. So this distribution is centered at H0 and has a unit variance. So this variance characterizes the variance of the noise. So under H1, if the transmitted signal is 1, then let's assume the observation follows another distribution, which is centered at 1 as unit variance. Okay. So if you can sketch these two distributions. Right, so this is distribution of this Fy condition on H0. And this is Fy condition on H1. So basically the intuition is that depending on the message sent by the transmitter, the receiver, the received signal is a perturbation of the original transmitted message. So intuitively, the received message should be concentrated around the original message. This is a reasonable model of the channel. And of course, in some real events, when we transmit -1, if in some real events, when the noise is happen to be very big, the observed signal can be very different from the original signal. So we model this as a Gaussian distribution around the transmitted signals. Now, given this information, we can simply leverage. So the setup is exactly the same as the binary hypothesis testing framework. Right? We have the prior information. We have two conditional PDFs. So we can perform the likelihood ratio test and derive the MAP rule, because we have mentioned last time the MAP rule actually minimizes the probability of error. Okay. So we do the MAP rule. The MAP rule will calculate the likelihood ratio. So this is the likelihood ratio test. Now we are given this one is 1. Right? So in this case, this reduces to the maximum likelihood test. Okay, now plug in this PDF functions. So we are given these two conditional PDF functions under different hypotheses. Right? They are different Gaussian distributions. So just plug them in. Under H1, this PDF follows Gaussian distribution centered at 1. So the PDF function is 1 over square root 2 pi e to the power negative y minus 1, because we are now centered at 1 divided by 2, because we have unit variance, divided by the denominator, which is under h naught, while this Gaussian distribution is centered at negative 1. Okay, so it's different. Okay, so it's these two, the ratio between these two Gaussian PDFs. One is centered at 1, another one is centered at negative 1. And then you simplify this term, right? Exponential divided by exponential. There are a lot of terms can be canceled. Okay, simplify it. You actually get e to the power of 2y. Okay, that's the ratio between these two. Now the decision rule says that this ratio should be compared with the, in this case, threshold is 1 with this threshold. Okay. And we can further simplify that e to the power of 2y compared with 1. So it depends on the sign of y. If y is bigger than 0, then this one is bigger than 1. Otherwise, it's less than 1. So this decision rule is equivalent to y, comparing y with the threshold 0. Okay, right. So the decision rule is very intuitive. I look at my observation, because this is the distribution of the two observations of the observation under different transmitted signals. Right? They are symmetric, and they are symmetric with regard to the original point 0. Now, so the decision rule is very simple. I look at my observation. If it is positive, then likely the transmitted signal will be h1, which is 1. If it's negative, then likely the transmitted signal is negative 1. Okay, but this decision rule is derived under the condition that these two prior probabilities are the same, meaning that we are likely to transmit negative 1 and 1 equally likely. Of course, if you change this assumption, let's say this threshold is not equal to 1, then here this decision rule will be a little bit different. Okay. So depending on the prior information, the threshold, the MAP threshold will be different. But in this case, this decision rule matches our intuition, depending on the sign of the observation. Because 0 is the midpoint between negative 1 and 1, right? So this is intuitively, this is how the decision rule chooses the threshold. Right, so this is the MAP rule. In this case, it's very simple. Now, now we have this decision rule. Let's calculate the probability of error. Right, because when you make these decisions, think about that. Now the decision rule says that if we observe a positive signal, then we decide it's 1. Okay, if we observe a positive signal, then we decide it's 1. But sometimes this signal could be the case that we are actually transmitting negative 1, but somehow there's a real event, there's a large noise, and the large noise perturbs the signal to be positive, right? So this is the case when we can make mistakes. And similarly, if we observe a negative observation, then this MAP rule will decide negative 1. But it could be the case where we are transmitting 1, but due to a large noise, we actually observe a negative signal. Okay, so these are the possible mistakes made by the decision rule. So the decision rule last time we mentioned how to calculate that. It's basically we need to divide it into two complementary cases. The first case is when we transmit H naught. Okay, when we transmit H naught, and then our decision rule gives H1. So this is when we transmit H0 -1, and conditioned on this transmitted signal, our decision makes a different decision. This is this is one type of error. The other type of error is when we transmit H1 and then conditioned on this transmitted signal. We decide H0. Okay. So these are the only two cases of where we can make mistakes. Okay, then let's look at each term. Probability of H0 is given as 1/2, so it's 1/2 here. And look at this one. Condition on H0, so we are looking at probability. This is a conditional event. We're conditioning on the transmitted signal H0. And this event, the decision rule decides H1. So we go back to decision rule. This is a decision rule. In order for the decision rule to decide H1, we must have the observed signal must be positive. So this event is actually equal to y bigger than 0. Because this is our decision rule, right? We will decide H1 whenever we observe a positive observation. So this event is translated into this one. And for the second term, same thing. So it's 1/2. So we are conditioning on H1. And now we are looking at the decision rule, decide H0. And from the decision rule, we know that it means y, the observation, must be negative. Okay. So we need to calculate these two conditional probabilities. And look at this one. The probability of the observation bigger than 0 conditioned on H0. Right. So if you look at this figure, conditional on H0, the PDF of the observation is given. It's a Gaussian centered at -1. And we want to calculate the probability that y is bigger than 0. Right? So that corresponds to, let me draw it here, this one. So this is the PDF of y conditioned on the transmitted message H0. Right? So it's a PDF centered at -1 as unit variance. Now, given this conditional PDF, we need to look at the probability of y bigger than 0. Right? So from this figure, you can see it corresponds to this area. So under H0, y has this distribution, and then we look at what is the probability of y bigger than 0. So it is this shaded area, right? And for the other case, it's the same. Under H1, the PDF of y is given as a different Gaussian centered at 1. Okay, and we need to look at the probability when y is less than 0. So it corresponds to this shaded area. So these are the cases where we make mistakes, right? This means we are transmitting H naught, the transmitted signal is here, but the observation somehow is positive. So the decision rule will decide H1. This is a mistake. Okay, and here is the same thing. We are transmitting 1, but if the decision rule, if the observation is negative, then we will decide H naught, which is a mistake. So we just need to calculate these two integrations. Okay. So write it down as 1/2. This shaded area, I can use CDF functions. Okay. It's 1 minus the CDF of y condition on H naught 0. So this shaded area is 1 minus this shade, the left shaded area. So this is CDF evaluated at 0. And this is the conditional CDF under H naught. But we know this CDF is basically the CDF of such a Gaussian distribution. And this one is simply the CDF of this Gaussian at 0. Okay, and we know that this random variable follows -1, 1. Okay, so we can normalize it. We can use the CDF of the standard Gaussian to represent everything. So this CDF of at 0 is equivalent to phi using the normalization formula that we introduced last time. Okay. This one is the CDF of the standard Gaussian random variable. Well, inside we need to normalize this this variable. So 0 subtract the mean is -1 divided by the variance. Okay. So this is the CDF, corresponds to CDF of normalized Gaussian. And for here, this one, it follows this Gaussian distribution. So we can, again, do a normalization. So 0 subtract the mean. Now the mean is 1 divided by the variance 1. Okay. So continue. Is 1/2 1 minus phi 1 plus 1/2 phi -1. And these two has a relation, phi 1 and phi -1. If you look at the centered Gaussian, phi 1 means, okay, so phi -1 is this shaded area. And phi 1 is this shaded area. So we can, by symmetry, we can see that 1 minus phi 1 equals to phi -1. So 1 minus phi 1 gives this part. And this is phi -1. These two shaded area, they are the same. So using this, so these two, they are actually the same. And using this equality, okay, the probability of error is phi -1. Well, phi is the CDF function of the standard Gaussian random variable. Okay, 0 mean unit variance Gaussian random variable. So you can check the table and calculate this number. So it corresponds to a number. So this is the probability of error of this entire system, of this binary communication system under the MAP rule. Okay. You will see similar problems in the homework. So you just follow these standard steps. First, derive the MAP rule. And then following these steps to calculate the probability of error. Okay. Make sure you don't make mistakes. If you go over these terms one by one, okay, they have different distributions, and we are conditioning on different hypotheses. But once each case is clear, calculating this probability should not be that hard. So in most cases, when we model the PDF as Gaussians, in the end, your result can be simplified by using the CDF function of the standard Gaussian. Okay, so this is everything about hypothesis testing. So next, we are going to talk about expectation and functions of random variables. So the first thing is expectation of random variables. Or we sometimes call it the mean, okay, in the classic way. Or the average, what is the average of, or the mean of the random variable. But the formal way is to say expectation. Okay. So the expectation of a random variable is defined as follows. So the notation is expectation of a random variable, capital X. Okay. Now, if this X is a continuous random variable, it has a PDF. So we take integration integrating over X times the PDF, okay, over the entire real line. So the expectation, intuitively, we're looking at what is the expected value of this random variable, right? So we do a weighted integration or weighted sum. We sum up or integrate all the realizations of these random variables, weighted by their corresponding densities. Okay. If a certain realization has a higher density, that means we have a higher chance to get to that point. So this has to be a weighted average. Okay. And the weights are specified by the densities, PDFs. Once we perform this weighted integral, we get the expected value of this random variable. Now, if X is discrete, then we simply replace integration by summation. Over all the possible outcomes, realizations of this random variable. Okay. So this is so these are standard definitions. A simple example is that what is the mean or the expectation of the outcome of rolling a failed die. You roll a failed die, what is the expected number that you can get? Well, so we know we have 6 different outcomes. Right, and each has a probability 1/6 because it's a failed die. So we just leverage the discrete formula, expectation formula. So expectation of X is sum over each realization. So the first realization is 1 multiplied by its probability mass. Okay? And we go to the second realization multiplied by the probability mass up to the 6. You can get the number 3.5. Okay. Yeah.
You get like 3.5. That's the expected value.
Yeah.
Like a lot of times.
No, this technically this means that, yeah, that's a good question. So this you can see that the expectation, this is a value. This value may not necessarily fall into the outcome space, right? You cannot roll a die get 3.5. You can only get integers. So the expectation is a statistical, it's a kind of statistics that gives you an understanding of the average outcome. So basically, technically this means that if you roll this die, let's say if you roll this die n times, and each time you get xk, okay. You roll this die for n times, each time you get xk. Okay. Each xk can be these integers, and you compute the empirical mean of your observations. Okay. And then you push this number to infinity. Basically, you roll this die for infinite many times. You compute the empirical mean. This should give you the expectation of this random variable. So it's a limit of an empirical evaluation of the average case. So this does not necessarily fall into the outcome. Now, the other one is when consider random variable, which is a Gaussian random variable centered at mu with standard deviation sigma. The question is, what is the mean or the expectation of this random variable? Well, we all know the mean is mu, but let's prove that. It is not obvious because this essentially says that this random variable follows such a Gaussian distribution. This is a complicated distribution. And we need to show that somehow the mean is this simple value mu, right? So the mean, and this is a continuous random variable. So we calculate the mean by integrating x times fx dx. And this could be complicated And let's write it down. Okay. But this x and dx, I know we can combine them into a quadratic term. And then we can integrating, if we make this equal to the exponent of this exponential, then I think the integration should be fairly easy. So let's rewrite this as we need to make it something look like this. So let me do x minus mu right? I can add a mu for free because this does not change the. Okay, why can I do that? Because I'm integrating over infinity. Okay, I missed the term here. So I want to create x minus mu so that combining with this one, I have x minus mu squared. So if I subtract mu here, I need to add mu. Right, it's the same. And with this one, combining with here, I can add mu for free, subtract mu for free. This one, dx minus mu, I can get a quadratic term. So this, and then I do a change of variable and let y to be x minus mu. So after change of variable, this equals to y. So you can combine these two, so you get a dy square, and you can make it negative y square over 2 sigma square. Okay, and then you take a integration over an exponential function. That can be done. So in the end, yeah, this term, which I will skip, you actually get 0. This term disappears. Whereas this term is integration of e to the power of negative quadratic x square. So this one, I think we need to rely on some integration formulas. Right? This one turns out to be mu. This integration turns out to be mu. So in the end, the answer is mu. And you have to refer to some references for this integration. Right, so this is how we calculate the mean or the expectation of random variable. We have to follow the PDF or PMF and calculate following the formula. In the lecture notes, there's another example which I will not go over here. It's the find the mean of this binomial distribution. So following the formula, you have to do sum over k probability x equals to k. So it's total of n trials, each trial succeeds with probability p. Binomial distribution characterizes the number of success, right? So the number of success can be 0 to n. Right? So each realization is k, and this is corresponding probability mass. This is specified by the binomial distribution. So it's sum over k, the number of success. Well, if we succeed k times the corresponding probability is n choose k, this is binomial distribution. Now we succeed k times, we fail n minus k times. Okay. And then you have to work out this summation. Okay. As the answer is n times p, but the calculation is pretty complicated. You can refer to lecture notes for the details. Okay. And intuitively, this makes sense because we perform independent experiments. Okay. Each experiment succeeds with p, probability p. So the number of success is the total number of trials multiplied by the success rate, right? The expected number of success. And then let's look at the linearity of expectation. The linearity says that it's very simple. If we have a bunch of random variables, then we have the expectation of the sum equals to the sum of the expectation. Okay. The important thing is that here, these random variables has no constraints. They are not necessarily independent. They can be arbitrary. They could be dependent, and this still holds. Okay. There's no requirements on this. You sum up any random variables, their expectation corresponds to the summation of the individual expectation. This is very useful because we will see in many problems, the random variable that we care about can be actually decomposed into some of smaller random variables. And instead of computing the entire random variable, the expectation of the entire random variable, which could be complicated, we can compute the expectation of the individual random variable and then sum them up. And computing the expectation of individual random variable can be much easier. Okay, I'll give you an example. The example is this binomial distribution example. Okay, right here we consider the mean, the expectation of this binomial random variable. And directly computing this following the formula is complicated because in the end we will have to work out this summation. A lot of combinatorics involved in it. But okay, let me write it here. Let's consider binomial random variable. This means the number of, so x is the number of success, right? The number of success over n trials, and each trial succeeds with probability p. Now I can do the following. There are n trials. I can list them here. For each trial, I can assign an indicator. The indicator is very simple. I look at the case trial. If the case trial is succeeds, I can define ZK as 1. If the case trial fails, I define ZK as 0. This is an indicator random variable for the trial K. So apparently ZK equals to 1 with probability P. Because we know each trial succeeds with probability P. So ZK equals to 0 with probability 1 minus P. Okay, this is an indicator random variable. And we know the distribution. It equals to 1 with probability P equals to 0 with probability 1 minus P. Then the number of success is simply a summation of ZK K from 1 to n. Right? Because ZK equals to 1, if that trial succeeds, now I sum up all these ZKs. Those ZKs who get 1 will give me the number of success over n trials, right? So this binomial random variable can be decomposed into a summation of a bunch of binary Bernoulli random variables. ZK is a Bernoulli random variable with P. Right, because it equals to 1 with probability P, 0 with probability 1 minus P. This is a standard Bernoulli random variable. Okay, so the binomial can be decomposed into a sum of these Bernoulli random variables. And in order to calculate the mean, I can leverage the linearity Okay, just need to calculate the sum of the expectation of each individual Bernoulli random variable. Now, Bernoulli is very simple. The expectation of Bernoulli random variables is very simple. Bernoulli is 1 with P, 0 with probability 1 minus P. So the expectation is 1 times P plus 0 times 1 minus P. So you get P inside. You sum over n p's, you get n times P. Right. So using linearity, this is much simplified. You don't need to compute all those combinatorics. So this tells us that sometimes decomposing the random variables, especially when we compute the mean. The reason that we consider decomposition is because by the expectation is linear with regard to different random variables. So if you can decompose a big random variable into a sum of smaller random variables, then we just need to compute the expectation of the smaller ones. Let's look at another interesting practical example. So we have R red balls and B blue balls. In the bag. Now you select these balls one by one. Okay, without replacement. Okay, what is without replacement? You first pick a ball, could be red, could be blue, uniformly at random. Now, whichever ball you picked, you keep it, you don't put it back. So suppose the first time you pick a red ball, you keep it. The next time when you do the second selection, the second time you pick the balls, you will have R-1 red balls, okay, and the B blue balls, right? So intuitively, when we sample without replacement, the following trials depends on the previous ones, okay? Because you do not put them back. So depending on which number of balls you draw in the previous trials, okay, the probability that you draw different balls in the follow-up trials would be different. So this sampling is more difficult to analyze. If you do with replacement, meaning that every time you select a ball and then you put it back, then for every trial you will have your choice is from R red balls plus B blue balls. It's the same for every trial, right? But if you do without replacement, then it's very different. Okay, your trial will be depend on the history. Okay, so basically you start from you just randomly draw these balls uniformly at random, one by one, without replacement. Find these expectations. The number of red balls that comes up before the first blue ball. Okay. This is a random variable X. Okay. I define this random variable as the number of red balls that I draw before I draw the first blue ball. But it is random because before you draw the first blue ball, you may have different, you may have already collect different number of red balls. So this X is a random variable. Now we need to compute the expectation of this random variable. So intuitively, this X, right, could be 0, 1, up to R. In the worst case, maybe the first time you draw, you get a blue ball. In that case, the number of red balls before you draw the first blue ball is 0, right? And in the best case, in your first R selections, you always get red balls. You are so lucky, you always get red balls. So And in your R+1 selection, you get a blue ball. So in that case, this X is R. You draw R, all the red balls before you draw the blue ball. Okay. So the first thing is the range for this random variable is clear. Now, to compute this random, the expectation, right, we have two ways. One way is to figure out this probability mass function, and then we follow this definition of the expectation to compute the expectation, right? So we know all the possible realizations of this random variable. So we can look at one by one. So look at first case. Can somebody tell me what is the probability of x equals to 0? How to compute the probability of x equals to 0? X equal to 0 means that we select 0 balls before the first blue ball. It's like in your first trial, you have to draw a blue ball, right? Because in every trial, you can only pick red or blue. If there's no red ball coming out before the first blue ball, then in your first trial, right, this has to be blue. So this is equivalent to say that you pick a blue in the first trial. Now, what is the probability of picking a blue in the first trial? What is the probability of picking a blue ball in the first trial? You have R in your first trial. You have R red balls plus B blue balls. Yeah, let's follow the intuition. You have B blue balls. In total, you have B plus R. So this is the probability. Okay, now you do the second one. X equals to 1. This means that you select one red ball before the first blue ball. So actually, the only possibility is that you first select a red ball and then you select a blue ball. Okay. So in your first trial, you select a red ball. So at least X equals to 1. And then in the second trial, you have to select a blue ball so that X will not grow further. Okay. So this corresponds to the probability where you have a red followed by a blue, right? I don't know if this notation is makes sense. So red in the first trial and blue in the second trial, in the second selection. Now tell me, what is the probability of selecting a red in the first trial, blue in the second trial, without replacement? Well, you have to do this one by one. In your first trial, the probability of selecting a red ball is R divided by B plus R. Once you select the red ball in the first trial, in your second trial, you have R minus 1 red balls and B blue balls, right? So in your second trial, the probability of selecting a blue ball is B over B plus R minus 1. Right? So that is it. So we can do this forever. Now if you want to do 2, which means you have 2 red balls coming out in the first 2 trials and then followed up by a blue ball. Okay. And the probability is no, R. The first one is red, so it's R plus B plus R, and multiplied by the second one. The second time you choose a red ball, you have R minus 1 red balls. So this is the probability of choosing the red ball. On third time you choose a blue ball, you have total B blue balls, but now your total number is R minus B plus R minus 2. Okay, because the first 2 red balls are never put back. Okay, so you can keep going and work out all the possibilities up to X equals to R, which means in the first R minus trials you have, or X equals to R means in the first R selections you always select red balls. Okay, and then follow up by the blue ball. Once you have this, you have the PMF of this discrete random variable. You can compute the mean. Okay, compute the means 0 times this probability plus 1 times this probability plus 2 times this probability, and so on. And this one has another approach. Okay. So this is approach 1. Well, we work out the probability mass function and follow the definition to compute the expectation. In approach 2 is a little bit tricky. So we can label the red balls as R1 up to RR. So we give them different labels. And I can define this indicator. If you look at the problem statement, we need to look at the number of red balls coming up before the first blue ball. So I can put a label on each red ball and assign that red ball a corresponding indicator. Okay. If that corresponding red ball coming up is selected before the first blue ball, then that indicator will is set to 1. Otherwise, it's set to 0. Okay. So I set this indicator to help me count how many number of red balls did we select before the blue ball. So II will set to be 1 if the ith red ball comes before all blue balls. And otherwise, 0 otherwise. Okay. Right. I give every red ball a label, and for each red ball, I define an indicator associated with it. This indicator tells me if this red ball is selected before all the blue balls. And apparently this is a random variable because this event that the ice red ball is drawn before all the blue balls. This is a random event. Okay? It may come out before all the blue balls, may or may not. It's a random thing. But with this indicator, the total number of red balls before all blue balls, that random variable is simply a sum of all the indicators. Right? Because each indicator tracks if the corresponding red ball is selected before all the blue balls. Okay. Summing up all these counters, indicators a counter. Summing up all these counters, we get the total number of counts of red balls coming up before all the blue balls. And therefore, this big random variable is decomposed into smaller ones. Well, each smaller random variable, for each smaller random variable, we only need to care about one single red ball. Right? So that's where things get simplified. Okay, so we just need to compute this expectation of II. Let's look at this one. Because II is a binary random variable, so the expectation is 1 times the corresponding probability. So it's a probability that II equals to 1 plus 0 times probability of II equals 0, which is II equals to 1. Now, what does II equals to 1 mean? II equals to 1 if Ri comes before all the blue balls. So we are essentially looking at the event, the probability of the event where the ice red ball comes before all the blue balls. Now, can you intuitively tell me what is the probability that the ice red ball is selected before all the blue balls? I mean, here you really don't know about the other red balls, right? The other red balls, they may be selected before Ri, may be selected after Ri, but so here we only care about the ice red ball and all the other blue balls. Do you have an intuition, a strong intuition that just follow your mind, follow your intuition? You don't need to care about all the other red balls, because in this sentence, we don't really care about all the other red balls. We only care about the ice red ball and all the other blue balls. Right, throw the rest of the red balls, throw them away. Now, what is the probability that you select this red ball before all the blue balls? Meaning that now if you throw the rest of the red balls away, you only have one red ball and the B blue balls, right? So in order to select this one before all the blue balls, you have to select this one in the first place. So it is just 1 over 1 plus B. It's just 1 over 1 plus B. Don't need to care about the rest of the red balls. But well, this is the intuition, and this intuition is correct. But if you want a very rigorous argument, you will have to work with the combinatorics. But I think intuitively following this sentence, right? We are not talking about the other Red Bulls. It doesn't matter it doesn't matter when the other Red Bulls are selected. They may be selected before RA, they may be selected after some blue balls. Doesn't matter. I only care about this Red Bull before all the rest of blue balls. So I can only focus on these B+1 balls. Okay. So this expectation is 1/1 plus B. So you go back. This is R plus 1 plus B. Okay. And I believe if you work on the first approach, you should be able to get same answer. But in the first approach, there are a lot of fraction numbers and you cannot really simplify them. I mean, these terms, they don't cancel. So you have to work out a lot of calculations to get the final answer. Hopefully, you can get the same answer. It's very simple answer. So I have 8 minutes left. So I want to briefly mention the relation between expectation and the CDF. So we know that the expectation is defined. Suppose X is a continuous random variable. We know that it is defined by integrating over the PDF. Okay. But there's an alternative expression, is to define it through the CDF in this way. So this is another way to define the expectation, but through the CDF. So one example is that if X is a positive random variable. Now, if X is positive random variable, this part is 0 because X has no density in the negative domain. Okay, so this integration is 0. So if X is a positive random variable, we have this. We have the integration equals to the expectation equals to this integration. But this one, this is a probability of X less than equal to X. Okay. So 1 minus that equals to the complementary event. So this is another way to characterize the expectation for positive random variables. For example, if we consider a positive random variable is exponential lambda, consider this positive random variable, which means the corresponding PDF okay, the PDF is specified by exponential distribution. So this is only supported on positive domain, on the positive domain. So for this random variable, we can use this formula to calculate the mean. You can also use the PDF formula to calculate the mean. They are the same. So here we use the CDF one. So expectations integration this one. And using the PDF function, you can calculate that this probability. You do another integration to calculate this probability. You can get these numbers, e to the power of negative lambda x. And then you plug it into this integration, you calculate this integration, you can get 1 over lambda. So which is the same as what you get by following the original definition of the expectation. And sometimes this one is very useful. Okay. So here we can see that expectation can be defined through integrating over either PDF function or CDF function. Okay. And I think next time we will talk about conditional expectation, which is very similar to, it's basically based on replacing this PDF or CDF, replacing everything by conditional PDF or conditional CDFs. Okay. So everything is now conditioned on another event. And that should be very similar to what we have discussed here. Okay, so I will hold office hours starting from 1 o'clock, because now I have an office. So if you want to come earlier, you can join the Zoom meeting anytime between 1 to 4 p.m. Okay. But I would appreciate if you can come earlier. Okay, so I will see you in the afternoon.